All right, so now that we have what we call the elongation matrix, we might actually come up with what we call the force matrix. And in this case, what we're going to, or force vector, I'm sorry, we'll say F sub S1, F sub S2, and S sub S3. And this is going to be kind of interesting. Mike and I have spent, well, this one confused me for quite some time. F sub Si is going to be the net change in the stored force of my spring, I. Do you recognize, if we go back over here, and this is where you actually have to visualize this. Do you recognize that there is a non-zero force stored in these springs in the equilibrium position at static? In other words, think about force as being able to do work. When I stretched those springs out and connected them, do you remember me doing that? And they were just sitting there, they were all stretched? If I cut one of those ends off, what would happen? The thing would go, which means it has the capacity to do work. Which means at rest, these forces, in terms of the capacity to do work, are non-zero. It's not like those springs are in their resting state, and if I connect it to something, they don't do anything, right? Those springs actually have forces. However, one of the nice things about mathematics is I can now reference that force as the zero force. I can say that with respect to that spring, every time the spring is at that exact length, that has zero net force. That is now my reference position for that location. Just like in Newtonian dynamics, can I say that this is the zero height? Sure. One of my mentors in life said all potential energy is with reference to a reference point. That must be true in gravitational potential energy, and it also must be true in spring potential energy. If that's true, what would the net force change be? What does Hooke's law say? Hooke's law says that the net force, this is why I get so angry with the way that I was first read Hooke's law, the net change in force is a function of how much you change the elongation of the spring. And what function is it in an ideal world? Yeah, maybe we say it's K2 times the elongation 2. Does that mean that the original net force is 0? No. It means that if this thing changes its length, the way that I calculate how much change in force is by multiplying it by the scalar K2 in this case, which is called the spring constant. Could you guess what the case is for the first spring? If I want to know the net force stored in spring 1, that would be a function of E1, which would be K1 times E1. What about the net force in spring 3? Yeah, go ahead.
What are we summing?
It's not that we're summing anything, it's that so formally speaking, we should use FU. Right? We should use the force in terms of the displacement. But the problem there is there are two what I would call absolute zero reference points that physicists impose on that model in the way that we think about it. The first absolute zero reference point is the way that you think about the changes in length of your spring. Every time that we think about that particular displacement, what they're saying is the top of the spring can't move. But in a dynamic system, that top of the spring could be moving all over the place. In which case I say, no, it's not the displacement that we care about, it's the amount of net change of length. The other net zero or absolute zero, Newtonian absolute zero, like they're literally putting a coordinate system in, is that usually physicists think about springs as being in the non-extended position to store zero forces. But that's not what's happening here. If I'm thinking about a zero force as the force stored in that spring at equilibrium position, if you look at the actual potential to do work, that spring can actually do work in that phenomenon. But what I'm saying is, mathematically speaking, I don't care about that. I will impose that position as the zero force position. And when I look at net forces, I'm looking for changes in the amount of force stored in that spring based on how much I elongate that spring. It's a subtle point. It's a very subtle point. What's the claim of Hooke's law in that paradigm? How do I calculate the first individual entry of that thing? This would be the spring constant for spring 1 multiplied by the elongation of spring 1 at any time t. What's the second one? And what's the third one? Here's a claim. I can now write this as a linear combination. What's the third one? Am I allowed to do that? Can I just throw in zeros randomly? Why? Because we know how to do math, right? Anybody see a linear combination of inner products? I mean, excuse me. I don't know if you want to do this by inner product or you want to do it by linear combination. Do you have a preference? Let's do it by linear combination. That's awesome. The first vector, let's go ahead and pick off the first vector there. Here I've got k1 e1 of t, 0, 0. Plus what? 0, k2 e2 of t, 0. What's the last vector? In this case, let's think about the scalars as the function, e. What scalar is multiplied by every constant in that vector? Would you agree that e1 shows up there, it shows up there, and it shows up there? What's the vector left over? k1, 0, 0. What's the next one? e2 of t. Anybody see a linear combination of column vectors with scalar coefficients stored in one of our most famous vectors that we've talked about in this modeling paradigm so far? What is it? First column is k1, 0, 0. Second column is, third column is. That is now a diagonal matrix with non-zero coefficients, all of which are positive. That's one of the most sexy diagonal matrices we'll ever see in our life. It's non-singular, it's got beautiful properties, these things come from actual measurements. This is a real world problem. What's the vector of coefficients? Could you guess how we write this then? If we're looking at the internal net force change in our springs, I can write this as a matrix vector product. The vector is E. Can you guess what we call the matrix? Wouldn't it be cool if we call it K? No, we don't call it K. We call it C. We don't call it K because there's this thing called a stiffness matrix, and that thing is A transpose C A, and we're going to get to that in just a second. That stiffness matrix shows up. You remember this? For those of you who've taken 2A? Sorry, should be a little careful. I think you all use the damping coefficients, right? What? Math classes transfer? No way. Yeah, we're going to do the vector version of this thing in this class. We won't get to, this is actually a quadratic eigenvalue problem. My PhD thesis was designed to work on this problem people to this day haven't solved this thing. That matrix K is this matrix, so we don't use K here because K is used in a very special thing in mechanical, civil, electrical engineers. It's something called a stiffness matrix. What we call this thing is C because that C shows up in many different contexts, right? It has a name for sure, and we'll come back to that. It would make sense to call it K because the K coefficients from my spring constant are along that diagonal.